Soil consistency refers to the resistance of soil to deformation or rupture under applied pressure. Soil consistency is vital for tillage and engineering. It is determined by the forces of cohesion and adhesion, which change with soil moisture. For example, soil can be hard when dry, friable when moist, and plastic when wet. Soil consistency as a result of cohesion is highest in clay, followed by organic matter, silt, and then sand. Several factors affect soil consistency, including moisture, type of clay, texture, organic matter, structure, sesquioxides, and calcium carbonate. Montmorillonite clay results in higher consistency than kaolinite. Consistency also increases with fineness and the presence of organic matter, sesquioxides, and calcium carbonate. Forms of soil consistency include hard, harsh, and coherent in dry soil due to cohesive forces. Soft and friable consistency occurs in moist soil, where water molecules decrease the coherence between particles. Friability is best for tillage operations. Plastic consistency in wet soil allows it to be molded into a shape that is retained. Sticky soil adheres to objects, and the sticky point is the moisture content when soil ceases to stick. Viscous soil flows under pressure or gravity, making tillage impossible. The field test for stickiness of wet soil involves pressing and opening your fingers to rate the soil from non-sticky to very sticky. The field test for plasticity of wet soil involves rolling the soil into a long, round strip to determine if it is non-plastic, slightly plastic, plastic, or very plastic. Moist soil consistency is tested by crushing the soil between the thumb and forefinger to determine if it is loose, very friable, firm, very firm, or extremely firm. The field test for dry soil consistency is done by trying to break air-dried soil and rating it as loose, soft, slightly hard, very hard, or extremely hard. Soil plasticity is the property that allows clay or soil to take up water to form a mass that can be deformed into any shape and maintain that shape after pressure is removed. Soils with more than 15% clay typically exhibit plasticity, depending on the clay type and organic matter content. The plate-like shape of clay particles and adsorbed water provide plasticity. The indices of plasticity include the upper plastic limit, the lower plastic limit, and the plasticity index. The upper plastic limit, or liquid limit, is the moisture content at which a soil ceases to be plastic and begins to flow like a liquid. This limit is important for soil classification in engineering. The Casagrande apparatus, a liquid limit device, is used for determining the liquid limit. The lower plastic limit, or plastic limit, is the lowest moisture content where a soil can be deformed without cracking. This is the upper limit of moisture content for most tillage operations. The plasticity index is the difference in moisture content between the upper and lower plastic limits. It indicates the range of moisture content over which a soil remains plastic and is an indication of soil compressibility. The plasticity index defines the range of water content where the soil is in a plastic state, situated between the liquid state and the semi-solid state. The shrinkage limit is the lowest water content at which soil is fully saturated. Below this limit, the soil begins to dry up at the surface. This scene is blank. Index properties of soil, like the liquid limit, plastic limit, and shrinkage characteristics, are significant for engineers. A high plasticity index can indicate poor roadbeds or foundations. The coefficient of linear extensibility, or COL, quantifies the swell-shrink property of certain soils. It measures the percent reduction in the length of a moist soil bar upon air drying. Soil compaction is the process of increasing bulk density and reducing pore volume through applied pressure. Soil compaction involves the destruction of macropores, the rearrangement of solid particles, and the compression of air within the pore spaces. This scene is blank. The degree of compaction depends on factors like the nature of clay minerals, water content, type of exchangeable cations, amount of energy applied, and extent of soil manipulation. Dry soils are hard to compact due to the incompressible nature of particles and high internal friction. Increasing moisture content decreases cohesion and internal friction, which facilitates compaction. Proctor moisture content is the moisture level at which maximum compaction occurs. Compaction increases with moisture up to this maximum point, then decreases with further moisture increases. The standard Proctor test is used to determine the optimum soil moisture content for maximum compaction. A plow sole is a compacted layer beneath the tilled layer that restricts root penetration. Management involves preventing its formation or breaking it up through chiseling, subsoiling, or deep plowing. Compaction of coarse-textured soils can sometimes be beneficial for better seed germination and efficient utilization of water and nutrients. For engineering, soil compaction provides strength for stable structures. Different equipment is used for different soil textures, such as sheepfoot rollers for clayey soils and vibrating rollers for sandy soils. Clay soils with swelling silicate clay are unsuitable for foundations because they tend to return to their original position after external pressure is removed. Soil compression is the change in soil volume under an applied stress. Compression increases with moisture content to a maximum and then decreases with further increases. Soil strength is the measure of a soil's capacity to resist applied pressure without deformation. Soils with insufficient strength can lead to the collapse of engineering structures, such as earthen dams or pavement sliding on unstable land. The strength of cohesive soils decreases under wet conditions and increases when the soil is dry and compacted. The direct unconfined compression test is a simple laboratory method for measuring strength.